Hello and welcome back. I haven't made one of these videos since March of 2020, and it is Christmas Eve of 2021 today. But the last video that I made in March was before the vaccine. It was before very much was known about coronavirus and transmission. And in the meantime, so much information has become available, plus some of the characteristics of the disease, I think have given cause to revise the model that we've had in the past and try to answer some of the questions that seem at the moment very mysterious. So these are the videos that I did in the past. I will see if I can maybe paste this list into the video, into the comments, but you can go and look at any of the previous modeling. I anticipated many of the characteristics of the disease at the time. In the original model, immediately when one looks at this kind of a disease where antibodies are produced by the body, we think of a disease with characteristics of being susceptible and then becoming infective and being able to spread the disease and then being removed either by immunity or by vaccination. Of course, at the time, there was no vaccination, so the R in our previous models would have been immunity. But everyone, of course, was anticipating the development of vaccines. We have seen that, in fact, you're susceptible to the coronavirus. Beta is the birth rate, so people are born susceptible beyond some initial maternal antibodies, potentially. There's a death rate for the susceptibles. But then by interaction with infectives, you become infected. But now the current information seems to imply that once you've recovered, there's a different death rate for infectives than for susceptibles. Obviously, people die from coronavirus, so this is an element that should be included in any kind of a model. And then you recover. When you recover from the coronavirus, according to what we think today, you can actually catch the disease again. So, in fact, this is one scenario where we could have a simple mathematical model that describes this kind of dynamics. So here the S and the I are the fractions of the population that are susceptible and infective, respectively. N is the total number of individuals in the population. And so we can see that here the beta N is the birth rate. Those people go into the susceptible population. The lambda is the contact rate, the number of effective contacts between an infected person and other people in the population. If they are susceptible, there will be a S fraction of those people who can actually catch the disease, and those are fractions of the population N. Then we have the delta 1 death rate for susceptibles, general death rate in the population, and then rho is the recovery rate. So those people go back into from the infective equation back into the susceptible population. You see in the second line here that we have a different death rate for infected individuals. This particular equation, we can actually solve it. So I wrote down the solution. And to see what the expected behavior is, if we look at this for a set of parameters that are similar to those I used in previous videos, you'll see the birth rate in the country, contact rate of 0.14, etc. I've got a tenfold death rate associated with the disease, and I introduce a small number of individuals into the population who are infectious and then see how the disease evolves. So we can see here that the difference between an SIS model and an SIR model is that the SIR model, once you achieve herd immunity, then the curve drops back down, whereas an SIS model, you feed those people back into the susceptible population. So, in fact, this perpetuates the disease and it keeps it going. Here A over B is actually the limit, here I've programmed this for 500 days. So the limit here is 0.498, so roughly 50% of the population becomes infective and stays infective. The R naught that we're fond of looking at, it tells whether the disease will die out or not. Here we see that it's almost 2. So that's the characteristic of an SIS disease as opposed to an SIR disease. So what we want to do here is refine this model so that we can incorporate any kind of this new kind of vaccination, because in the meantime, several vaccines have been developed, and we can vaccinate people. I hesitate to say immunize, but here's how the new model should look. First of all, people are susceptible to the first type. That means never had the disease before. Then they actually can become infective for the first time that they're infected. Then they recover and go into a second type of susceptible. So these people have had the disease. So in fact, their probability of catching the disease and transmitting the disease would be different from the S1 type. So we want to incorporate that into the mathematical modeling. And then those people in the S2 type can become infective, and we've included them in a type 2 infective that we can model. So we're still presuming that newborns go into the S1 class, never been infected before. Then we have Delta 1.1, Delta 1.2, Delta 2.1, and Delta 2.2 are the respective death rates in each of these categories. So that allows us to attribute a higher level of death rate depending on whether it's the first time you've been infected or the second time you've been infected, etc. So here we have an interaction of susceptibles with type 1 infectives that produce type 1 infections, and we have an interaction of type 2 infectives with S1 susceptibles, and that produces a type 1 infective as well. So those type 1 infectives can recover with a rate of rho 1, so they go into the second type of susceptible. And those people can actually become reinfected by interacting with a type 1 infective, or they can become reinfected by interacting with a type 2 infective. So at that point, then, they can recover from the I2 or subsequent infection and go back into the previously infected and now, again, susceptible group. Now introduce vaccination into the scheme. Theta, or rate of vaccination, takes people out of the susceptible 1 class and puts them into the susceptible 2 class. So it jumps over the first infection and gives them antibodies that are actually going to protect them as if they had had the disease. But in this particular scheme, they're not going to have the same disease characteristics. If they are infected, they'll have an I2 infective type. Now, the parameters that we went in, these are similar to the other videos that we've done just for the definitions. The S1 is the fraction of the population. I'm working now with fractions of the populations so that we can have a model that is in some way independent of what country we may apply this to. So the S1 is the fraction of the population that's susceptible and never been infected. I1 is the fraction of the population who are first-time infectives. S2, fraction of susceptibles that have recovered or been vaccinated. I2 are the types of population, fraction of the population who are repeat infectives. And then, as we saw in the scheme before, in the graphic scheme, lambda 1.1, 1.2, 2.1, 2.2 are the contacts of S1 with I1, S1 with I2, S2 with I1, and S2 with I2. So the 2 different types of susceptibles and the 2 different types of infectives and their interactions with each other. The deltas are the death rates of susceptibles of type 1, infectives of type 1, susceptible of type 2, infectives of type 2. Theta was the vaccination rate that we saw, and the recovery rates from I1 and I2 are rho 1 and rho 2, and beta is the birth rate. Initial 1 is the initial fraction of infectives that we introduce into the population, so we can see what the global evolution of this disease is. With that, we can actually write down equations using the same kind of logic that we did before, that all newborns go into this type 1 susceptible, that people die out of the susceptible is the second term on the first line, that there's an interaction with type 1 infectives or an interaction with type 2 infectives that produce new diseases. Those diseases go into type 1 infective. Then theta, those are the people in the first end of the first line, people who are vaccinated and move into the type 2 susceptibles. So the type 1 infectives, either they die or they gain people from the first infection, or they lose people who recover. So the type 2 infectives, they either die or they have people recover, who all the recoveries go into the type 2, the row 1 and row 2 terms there. They gain people from vaccination and they lose people from new interactions of type 2 susceptibles with type 1 and type 2 infectives. Finally, then, the rate of change of the number of type 2 infectives, they can either die with a rate of delta 2, recover with a rate of rho 2, or gain by interaction and infection of type 2 susceptibles. So the n prime over n is a term we've seen in the models before, that we're going to use to, in fact, simplify the model somewhat. I have programmed this as we did in previous videos, and I'm looking at solutions now of the infective type 1 and infective type 2. So looking at that, this is for the first run where we took the lambdas to have all the same values, so we're not differentiating between any kind of behavior. There's no different masking or social different distancing done between the different types of infectives or susceptibles. I've taken all the lambdas to be 0.14, which is what we had in the simple one susceptible and one infective disease types. So you can see here that a characteristic, if we only look at the type 1 infectives, that's the red curve, because of losing those people on the red curve to go into the second type of susceptibles, they're recovered. I did not put any vaccination into this because I wanted to compare the results with the original model, the simple model. And you can see that in the blue curve that we have exactly the same behavior as we had in the simple model, but here we can see that all those infectives of type 2 are really showing the same behavior that we had with the simple model, and the type 1 infectives will go up and die back down. So economically, we can see, we've seen that the hospitals are overloaded with primarily with the type 1 infected, and that's where the actual economic impact of the disease is coming from. But the disease impact, the fraction of the population that's actually infective, is going to be much more impacted by the type 2 infections. This means that we need to focus on how to, if we want to reduce the total occurrence of disease in the population, we have to focus on both types of infectives, the type 1 and the type 2. We simply can't let the type 2 infectives just go back to their usual behavior as we've seen in previous videos. So now, where can we intervene in the behavior? Should we intervene in infective of type 1 or should we intervene in infective of type 2? So I presumed that we could influence the type 1 and reduce that. So this particular model takes the type 1 behaviors, the lambda ones, 1, 1, and 1, 2, and cuts them in half. So we have half the number of contacts per unit time. And we can see that we have qualitatively the same kind of behavior, but the type 2 infectives go up to the same level. The type 1 infectives, let me jump back to the previous graph. Here we see the red curve went up to 0.15, and here the red curve in the second run. When we reduce the lambda ones, then the red curve goes down to 0.1, whereas the blue curve takes longer to get up high, but it still goes up to about half the population. So by reducing the contacts, we do have an effect on the number of type 1 infectives, which means we can actually influence the number, the overloading in the hospitals and that sort of thing. But we still have qualitatively a problem with the type 2 infectives. Now let's go back and see what happens if we focus some kind of attention on the type 2. If we do that, now I've switched, although the lambda that I picked for lambda 2s, I picked 0.08 instead of 0.07. I'm going to do 0.07 next, but here I did 0.08. And we see a fairly dramatic effect if I do nothing more than switch the influence on behavior into the type 2 instead of type 1. I still have a lower number of type 1 infectives, but the type 2 infectives actually decreases quite significantly in the behavior. Notice that we still have endemicity, that is, the disease still stays in the population, but it's a much, much lower rate. Here I've improved my behavior. I've done masking and social distancing for my already vaccinated people, the ones who are in some kind of second or subsequent number of infections. Now, if I reduce that behavior even more to 0.7, I reduce the curve even more. So now here, actually, this is a bit misleading. The 0.08 is probably best because I had to compare the two behavior modifications, lambda 1s and lambda 2s, because here in this particular graph, I have introduced a very low level of immunization, so that's going to improve these curves a little bit more, as well as the behavioral change going down to 0.07. Now let's see what happens when we start to increase our vaccination. I'm going to leave the behavioral level at 0.07, but I'm increasing the vaccination. You see that the curves start going down fairly significantly with the vaccination. Here I've increased the vaccination as well, and I'm getting even lower curves. My vaccination goes up to theta equals 0.005. Let me back up a little here. The first vaccination was 0.0001, then 0.001, and then 0.025, and now 0.005. And now I'm really killing the disease. Whether that 0.005 level of vaccination is achievable or not is also a good question. It depends on the country and then the population, and that's the rate of vaccination per day. And then here, if I went up to 0.01, I would have killed the disease. So the difference here is that we have, in this particular model, is here we have, going back to our scheme, we have a model that takes the two different types of susceptibles and two different types of infectives into account. We can see that what seems mysterious here in the increase in the number of cases is a characteristic of the SIS disease, but it's also a characteristic of our S1, S2, I1, I2 model. We would expect to have an explosion of the number of Omicron cases. Here, Omicron would have an R naught much higher, most likely. But we can see that this is a qualitative characteristic kind of behavior that we would expect with an SIS disease instead of an SIR disease. We're not getting the SIR effect of herd immunity and dropping down simply because those people are not removed from the susceptible infective interaction. They go into this more complicated schema here where we have different types of susceptibility and different types of infectiousness. So the advantage here, once we do this model and we start looking at the effect of changing behavior in the I1, is maybe it's effective but not so effective for the disease, effective for the hospitals. On the other hand, changing the behavior in the I2 infectives, that is, maintaining some kind of masking, maintaining some kind of social distancing, is going to have a higher effect. And then if we vaccinate in addition to that, we actually can, by a higher rate of vaccination, we can lower that curve significantly. So that's new considerations in the transition of coronavirus with the effect of Omicron and the fact that we don't have really the SIR type characteristics that we thought we did. That's all for today. Thank you very much. Maybe see you in another video. I did not anticipate doing another video, but the new information about the disease actually, I think, warranted it. Thank you very much. Bye.